Welcome to the next lecture on wireless communications. Today we will look at equalization techniques. First, a brief outline for today's talk. We will start with a brief survey of equalization techniques, followed by a study of linear equalizers. Then we will move into the domain of nonlinear equalizers. We will look at the decision feedback equalizer or DFE, then the maximum likelihood symbol detection, and finally the maximum likelihood sequence estimation. Finally, we will talk about algorithms for adaptive equalizations. The three important algorithms that we will study are the zero forcing, the least mean square or LMS, and finally the recursive least square algorithm. So this is the brief outline for today's talk. Let's recap what we have learnt so far. In the previous lecture, we saw that the channel impairments because of multipath and hostile mobile environments can be overcome using one of the three techniques: equalization, diversity, and error control coding. However, we can use them individually or in tandem. Then we looked at the basic fundamentals of equalization, followed by a brief structural investigation of the adaptive equalization technique. Now, what is the block diagram for a generic adaptive equalizer? We saw last time that the original baseband signal xt goes through a modulator, then through a transmitter, finally through the radio channel, wherein there is a distortion and noise and also fading effects, which is received back at the receiver RF receiver front end, down converted to IF stage, followed by the detector matched filter. Finally, there is an equivalent noise added and it goes through the equalizer. The job of the equalizer is to undo the effect of inter-symbol interference. Now, please note that this reconstructed message data dt we saw last time is an estimate and should match x of t. If we use dt and use it in a feedback loop to adjust the weights of the equalizer, we get into the domain of nonlinear equalizers. However, if this feedback is not there, we just have a feed forward loop, then it is a linear equalizer. We will talk about these two in greater detail today. Now, last time we also saw the simple working of an adaptive equalizer. Why adaptive? Because the channel is changing with time, and so the weights must be updated periodically. So, the received signal yt is the convolution of xt and the composite impulse response f star t, plus added with the baseband noise n subscript b. Everything is analog in time domain. And we saw that if the impulse response of the equalizer is h equalizer t, the output of the equalizer is simply given by this equation: xt convolved with an effective gt plus nbt convolved with h equivalent t. If you do the basic mathematics, we saw that in time domain, in order that the equalizer must work in the absence of noise, nbt is equal to 0. In that ideal scenario only, when only the distortions are because of channel effects, you have gt should be equal to the impulse function delta t, and in the frequency domain it should be h equivalent f star minus f equal to 1. So, if you have this condition satisfied in the frequency domain, then you are in business, you can equalize the channel. In a layman's language, equalization undoes what the channel does. Okay? It is an inverse function, it is an inverse filter, which has a problem also, because if you have deep nulls in the frequency spectrum of the channel, then you tend to amplify the noise in those areas as well, and therefore the need for a non-linear equalizer. So, we realize that equalizer is in fact an inverse filter of the channel, but in the absence of noise. So, clearly if noise is present, there will be some predictive error which you cannot remove completely. If the channel is frequency selective, what does the equalizer do? It tries to undo the effects of channel, that is, it enhances the frequency components with small amplitudes and at the same time attenuates the strong frequencies in the received frequency spectrum. So, it reverses whatever is done by the channel, and this is done in order to provide a flat, composite received frequency response as well as a linear phase response. Now, mobile channels are time varying. So, for a time varying channel, the equalizer is designed to track the channel variations, so that the above equation given here in frequency domain is approximately satisfied. In this slide, we have a generic block diagram for an adaptive equalizer. Please note that the weights here have two indices, 0, 1, 2, 3, 4 for the different weights, and the k represents the time index. Z inverse implies the delay. Yk is in the input, and this is multiplied by the weights added to get an estimate, d hat k. So, an adaptive equalizer is a time varying filter which must be constantly retuned. How do we retune it? We will look at some popular algorithms today. In the block diagram, the subscript k represents discrete time index. It can be seen from the block diagram that there is a single input yk at any time instance, and rest are the delayed versions. Exactly how many delays do we need? How many tap points do we need? It depends on what is the root mean square delay spread of your channel. If you can have a very large root mean square delay spread of the channel, then you need to have more number of delays and more number of tap points. It can only equalize to the delay built into the equalization, right. So, that is a direct correlation between the delay spread of the channel and how many weights in the equalizer and what are the delays here should there be. In fact, this necessitates the need to have some kind of an adaptive equalizer where the channel, if it has a very large delay spread, I should be able to use more number of delay elements and more number of tap points, and then when my mobile moves to a region where the delay spread is much shorter, I should be able to undo some of the stages and retain only the necessary number of tap points. We will see today that there is one kind of an implementation that precisely does that. But in general, the block diagram shown just before, which is called a transversal filter, it has n delay elements and hence n plus 1 taps, and consequently n plus 1 tunable multipliers, which we will call weights. Now, these weights can be complex weights. As pointed out earlier, the weights have a second subscript k to explicitly show that they vary with time and must be updated on a sample by sample basis or a block by block basis, that is for the whole weight vector. Now, how do we retune the weights? The adaptive algorithm is controlled by the error signal Ek. The error signal is derived by comparing the output of the equalizer with some signal dk, which is either a replica of the transmitted signal xk or which represents a known property of the transmitted signal, for example, constant amplitude. The adaptive algorithm uses this Ek to minimize the cost function and uses the equalizer weights in such a manner that it minimizes the cost function iteratively. So, it is upon you to define a cost function, and today we will look at a couple of definitions of different kinds of cost functions. One of them, the least mean squares algorithm, searches for the optimum or near optimum weights. The cost function clearly is the least mean square error. So, in an adaptive equalizer, the new weight is updated as follows: new weights is previous weights plus some constant gain times previous error times current input vector. This is one possible implementation, where previous error is previous desired output minus previous actual output. Here the constant shown here may be adjusted by the algorithm to control the variation between the filter weights on successive iterations. The process is repeated rapidly in a programming loop while the equalizer try to converge. Now, please note how soon does it converge, because only then I can have a good estimate of what was sent. If it takes too long to converge, then I may not be able to use it in real time. This is one of the factors which will help in deciding which kind of equalizer to pick up. So, rate of convergence. When the convergence is reached, the algorithm freezes the filter weights. Now, let us have a quick survey of equalization techniques. Equalization techniques can be broadly classified into the following: linear equalizers, nonlinear equalizers. These are classified based on how the output of an adaptive equalizer is used for subsequent control of the equalizer. So, if we have a feedback loop, if we use the estimate of dk, that is dk hat, and feed it back to update the weights, then we get into the domain of non-linear equalizer. Whereas, if we only have the forward loop and there is no feedback, then it is a linear equalizer. We will soon see that the linear equalizer can be easily implemented as a finite impulse response FIR filter. In general, the decision maker determines the value of the digital data bit being received and applies slicing or thresholding operation, which is a non-linear operation for obtaining the value of dt. So, there is a thresholding operation that will happen at the decision making level, and only then you get an estimate of dt. In linear equalization, the output signal dt is not used in the feedback path to adapt the equalizer. However, in nonlinear equalization, the output signal dt is fed back to change the subsequent outputs of the equalizer. This is a basic difference. Now, there are many filter structures that are used to implement linear as well as nonlinear equalizers, and decoupled to that, there are numerous algorithms for each structure to adapt the equalizer weights. So, there are two components to an equalizer design: the structure and the algorithms to update the weights, and there is no link between the two. You can choose one structure and use another algorithm to update the weights. Now, let us classify our equalizers. So, the equalizer can be broadly divided into linear and nonlinear types. Linear, no feedback from the dk; nonlinear, yes, there is a feedback. Now, let us talk about the structures. We have already seen the transversal structure. Again, we will talk about it, but linear equalizers have a transversal structure possible, or also a lattice structure possible. We will talk about these again in greater detail. At the other end, the nonlinear equalizers can either be a decision feedback equalizer or a maximum likelihood symbol detector, or an MLSE, sequence estimation, maximum likelihood sequence estimation. Again, these three can be either implemented using a transversal filter or a lattice filter or a transversal channel estimator. Now, for each of these structures, you have the flexibility to use various kinds of algorithms to quickly update the weights. Most of them are recursive algorithms. You could either use the zero forcing or LMS least mean square or RLS recursive least square or the variations thereof. Again, you have a possibility to use different kinds of algorithms depending upon how fast they are, what is the minimum error they give, how much power they consume, right. So, we will talk about how to pick and choose an algorithm for a particular type of structure later today. But this gives you a brief overview of how equalizers can be classified in terms of linear, nonlinear, structure and the type of algorithm used to update the weights. Now, first let us talk about the linear transversal equalizer, one of the simplest implementation and a popular one. The linear transversal equalizer is the most common equalizer structure simply because of its simple structure. The linear transversal equalizer is made up of tapped delay lines with the tap spaced at a symbol duration Ts apart. So, the delay element gives a delay of T of S. Assuming unity gain of the delay elements and the delay equal to T of S, the transfer function of the LTE, which is the linear transversal equalizer, can be written as a function of delay operator e raised to the minus j omega Ts denoted by z raised to the minus 1. The simplest LTE uses only feed forward taps and transfer function is a polynomial of z inverse with many zeros, but poles only at z is equal to 0. This is called a finite impulse response or FIR filter. So, a linear transversal equalizer can be simply represented as a FIR filter. There is no feedback. In this slide, we have a simple structure for the LTE or linear transversal equalizer. As you can see, we have the delay elements. Ts represents the symbol duration. Here you have Yt plus Nbt. Nbt represents the baseband noise. Please remember, the equalizer is designed to work in the absence of noise. In the presence of noise, there will be some predictive error. Clock with period tau. Here we have the tap points, and based on that you can calculate and obtain your dk hat, the estimate of dk. So, this is the basic structure of linear transversal equalizer. You have delay elements and you have the tap points. Now, let us talk about the IIR filter based equalizer. If the equalizer has both feed forward and feedback taps, its transfer function is a rational function of Z inverse and is called an infinite impulse response or IIR filter with both poles and zeros. These IIR filters tend to be unstable when the strongest pulse arrives after the other pulses. So, IIR filters tend to be unstable sometimes for mobile scenarios. Here is a block diagram of a simple IIR filter based equalizer. Please note, Yt is the input waveform. We have removed the noise part right here. Now, here you have again the delays Ts. Then you have tap points. So, the A1, A2s and so on and so forth represents the forward tap points, and this is the feed forward taps. Here B1, B2, B3 and so on and so forth represents the feedback taps going here. Even though there is a feedback, please note there is absolutely no feedback from the D hat T. The D hat T is not being used to update the taps at all. Therefore, it is still a linear equalizer. So, there is a feedback path, but feedback for the taps alone. So, we have two loops, the feedback taps adding up here and the feedback taps adding up here and the feed forward taps adding up here to give you the estimate D hat T. Continuing with our linear equalizer, the current and the past values of the received signal are linearly weighted by the filter coefficients and summed to produce the outputs. So, it is a very simple implementation in hardware. Multiply with the weights and finally add them up. The shifting is usually done using shift registers. So, it is a very hardware friendly operation. If the delays and the tap gains are analog, the continuous output of the equalizer is sampled at the symbol rate and the samples are applied to the decision device, okay, where thresholding or slicing is done. If it is implemented in the digital domain, the samples of the received signal are stored in a shift register. Let us take another look at the linear transversal equalizer or LTE. Again, we have an input signal Y coming in here, right, and then there are certain number of tap points multiplied with the complex weights, add them up, and this is the decision maker, which is a thresholding device, and output is the decay. This is a simple structure of the linear transversal equalizer. Again,
can decay dash be a complex number?
Question being asked is, can decay hat be a complex number? The answer is no. At this time you have taken a decision about the bit, so it is already decided. So, this will not be complex.
And
Prior to that it can be complex. So, all these can be complex. Clearly they are complex, you are multiplying with a complex number, but whatever you do at the end you have to take a decision here, and for a very simplistic binary case you are coming up with a 1 and a 0 here. Please note these are the tap points delayed by T of S, the symbol duration, and the number of delay elements would be a function of what is the delay spread of the channel. The weights are complex as shown here. These weights must be updated by some method. The current in the past values of the received signals are linearly weighted by the filter coefficients and summed to produce the output. The output of the transversal filter before the decision making is given by this equation. D hat k is summation of the complex weights multiplied by the tapped delay values of yk. In this equation, Cn star represents the complex filter coefficients, also called as the tap weights. Dk is the output at the time index k. Yi is the input received signal at time t naught plus I t. T naught is the equalizer starting time. N equal to N1 plus N2 plus 1 is the number of taps. What are N1s and N2s? N1 is the number of taps in the forward portion, N2 is the number of taps in the reverse function. So, this sums up the general linear transversal equalizer. How you adjust the weights is a different story. But this should give you, if the weights are correct and optimal, a good estimate of what was transmitted. Now, let us talk about how good is it. The minimum mean squared error, which is the expected value of error squared that a linear transversal equalizer can achieve, can be worked out as follows. Expected value error squared is t over 2 pi integration minus pi by t to pi by t n naught over this f e raised by g omega t absolute value squared plus n naught d omega. This, the derivation is not being given here, it is available in most of the textbook. For example, Proekis gives a very good derivation for this one. Here the f e raised by j omega t is the frequency response of the channel. N naught is the noise spectral density. So, please note that it depends on the noise. I can do nothing about it. If I increase the noise power, I helplessly have to see that the mean squared error, minimum mean squared error goes up. I can do nothing about it. And if my channel is not so hostile, if I have a flat channel, right, then this becomes pretty handleable. You can work around it and you can lower your error. Now, let us look at another implementation in terms of structure for a linear equalizer. We will call it the lattice equalizer. There is a lot of information on this slide. Let us try to understand what is going on. Here you can see y, the input. Now, this input has been judicially divided into two branches. Here is the forward loop. Here is the backward loop. The forward loop is being characterized with f1k, f2k, so on and so forth till fnk. The backward loop has these coefficients b1, k minus 1, b2k, and so on and so forth till bnk. The delays are here, C1, C2 up to Cn, and this particular structure is called the lattice structure. We have these reflection coefficients k1, k2 up to kn minus 1. You add them up and you get d1t. We will just now show that despite this structure, the d1 hat will come out to be nothing but the delayed version of yk's multiplied by the appropriate complex weights. But there are certain very good advantages of the lattice equalizer which we will talk about. So, each stage of the lattice is characterized by the following recursive equation. So, if you go back and forth between the last slide and this slide, you can easily correlate that f1k is b1k is yk, that is the initialization factor, and then you have a recursive equation fnk is ynk minus summation I is equal to 1 through n. This reflection coefficient ki yk minus I is equal to this expression. So, if you go back here and try to correlate, you will be able to figure out how you can write yk in terms of the previous values. Similarly, bnk is written by yk minus n minus summation I is equal to 1 through n ki yk minus n plus 1, again comes from the lattice structure. This can be written as bnk is equal to bn minus 1 k minus 1 plus kn minus 1 k fn minus 1 k. Very simple relationship. Here k subscript n k is the reflection coefficient for the nth stage of the lattice. The backward error signals bn are then used as inputs to the tap weights, and the output of the equalizer is finally given by dk hat is summation n is equal to 1 through n Cnk Bnk. Okay, exactly what we are looking for. So, why do we have to go through that complex structure? We are finally getting what we expect, but why do we have to go for that structure? The first thing is there is a lot of numerical stability. We saw the IIR filters tend to get unstable mathematically. Here the lattice equalizer has numerical stability, then it has a faster convergence time, very important. Its unique structure allows dynamic assignment of the most effective length of the lattice equalizer. This is for the first time we are talking about the effective length required for the equalizer structure, which should be matched to the delay spread of the channel. When the channel becomes more dispersive, right, the mobile enters in a densely packed urban environment, the length of the equalizer can be increased by the algorithm without stopping the operation of the equalizer. On the other hand, only a fraction of stages is used if the channel is not very time dispersive. What is the main disadvantage? It is obvious. The main disadvantage of the lattice equalizer is its complex structure. But this is again a good linear equalizer that is used. But in general, linear equalizers have certain disadvantages. What are these? The linear equalizers do not perform well on channels which have deep spectral nulls in the passband. After all, what is an equalizer doing? It is trying to make an inverse filter, undo the effects. So, in the frequency domain, wherever there are deep nulls, which there are in most hostile wireless channels, it will try to have a very high value in the frequency domain, thereby giving a lot of importance to the noise present at those frequencies. It will amplify the noise immensely. To compensate for distortions, linear equalizers places too much gain in the vicinity of these spectral nulls and thus enhances the noise present in these frequencies, not good. So, nonlinear equalizers are used when channel distortions are too severe for linear equalizers to handle. That is where they step in. So, let us now move into the domain of nonlinear equalizers. The three effective nonlinear equalizer methods are as follows. The first, which is also a very common one, is the decision feedback equalizer, DFE. We will talk about DFE in detail, followed by the maximum likelihood symbol detection technique, and then the maximum likelihood sequence estimation, MLSC. We will talk about MLSC also. First, let us look at the decision feedback equalizer, the DFE. This is the general structure of DFE. The input signal comes in here and then it is delayed as always. And then you have the complex weights Cn1, Cn1 plus 1 and so on and so forth. This is your feed forward filter, also called as FFF or triple F. At this juncture you have decay and then you have a thresholding device and then you get an estimate. But what is interesting is, for the first time we take this decay after the decision device and feed it back to the feedback filter FBF shown here. Again, this has several delay elements and then the feedback filter coefficients F1 star and so on and so forth, adding up and going it. Right. So, somewhere the philosophy is to estimate the intersymbol interference, because you have already detected the past symbols. So, you can predict what are the intersymbol interference it will cause to the subsequent symbols and subtract it out. So, if you can estimate the intersymbol interference that will be induced by the current decoded symbol, and if your decision is correct, then it is possible for you to subtract out the ISI. So, that is the smart move that DFE does. So, in DFE, the intersymbol interference the present symbol induces is estimated and subtracted out before the detection of subsequent symbols. Okay. Fairly simple philosophy. If you already have the information, why not use it to cancel out the intersymbol interference it will induce. Now, the direct transversal form of the nonlinear equalizer consists of, as we have seen, the feed forward filter FFF. It is same as the linear transversal filter we have learned so far, and then there is this new element called the feedback filter FBF, driven by the decisions on the output of the detector, and its coefficients are adjusted to cancel the ISI on the current symbol from the past detected symbols. For DFE, the output is given by d hat k equal to summation n is equal to minus n plus n1 through n2 complex weights multiplied by the appropriately delayed input plus this feedback filter coefficients Fi multiplied by dki. Right. Please note here you are working on the delayed version of the decisions. What is your dk? Dk is the decision on a symbol being transmitted, and as you can take dk minus I, you delayed the previous. So, based on the previous symbols, you adjust the weights and subtract the ISI. Here Cn star and Yn are tap gains and the inputs respectively to the forward filter, and Fi star are the tap gains of the feedback filter, and Di, where I is less than k, is the previous decision made on a detected symbol. Note, feed forward filter has N1 plus N2 plus 1 taps, whereas the feedback filter has N3 taps. Now, again we have to talk about how good or bad is your DFE. So, we have to resort to the minimum mean squared error. So, the minimum mean squared error for DFE can be given by the following equation. Expected value of error squared minimum is e raised power t over 2 pi integration minus pi by t to pi by t log of this expression. Please note, we had a previous expression where both the exponential and logarithmic were missing. It can be shown that the minimum square error of DFE is always smaller than that of the linear transversal equalizer LTE, except when the absolute value f e raised by j omega t is constant. This value is the transfer function of the channel, n naught is the noise power. Again, we are helpless as noise goes up, noise power goes up, then your minimum mean squared error will go up and we can do nothing about it. Now, LTE performs well for flat channel spectrum. Here f e raised by j omega t is the channel spectrum that we are talking about. For a flat channel spectrum, our general linear transversal equalizer works well. But the moment you have severely distorted wireless channels with deep nulls in the spectrum, you have to have the decision feedback equalizer or a nonlinear equalizer to come to the rescue. What is important to note is the minimum mean squared error of DFE is always smaller than that of the LTE. Now, let us talk about the next one, maximum likelihood sequence estimation. The MLSE tests all possible data sequence using channel response simulator and chooses the data sequence with the maximum probability as the output. So, it was first proposed by Forney in way back in 78, in which he set up the MLSE estimator structure using the Viterbi algorithm. The MLSE state of the radio channel is estimated by the receiver using L most recent input samples. If m is the size of the input alphabet of modulation, then the channel has m raised by L states. The Viterbi algorithm then tracks the state of the channel by paths through the m raised by L trellis and gives at stage k the most probable sequence. So, it is some kind of a sequence estimation. Needless to say, it will be computationally very intensive, but you will get a much better minimum mean squared error. MLSE is an optimum equalizer as it minimizes the probability of sequence error. Please note there are two things. One is the probability of sequence error and one is the minimum mean squared error. The bottom line is the probability of sequence error should be minimized. It so happened that in earlier cases we have said, okay, we will minimize the minimum mean squared error, and then it will automatically lead me to have a low probability of error. Here for the first time MLSE works on minimizing the probability of sequence error. Right? So, in that sense it is an optimum equalizer. So, let us look at the block diagram of the maximum likelihood sequence estimation. Here, for a change, this is a different structure. There is the input YT, goes through a matched filter, and immediately you have a ZT. You sample it to get Zenith, and you work on the samples. So, you have this maximum likelihood sequence estimation, which is being implemented using a Viterbi algorithm, and then here you have a delay, channel estimator, and goes in a loop and adjusts the matched filter. Finally, after k stages, you get the estimated data sequence out. Now, let us focus our attention on the various kinds of algorithms for adaptive equalizer. These algorithms can be used both for linear as well as nonlinear equalization, and we will discuss them here in general for linear equalizers, though the analysis that we discussed today can be easily extended for the case of non-linear equalization. First, what are the factors which determine an algorithm's performance? First is the rate of convergence. We have discussed this before. All of the algorithms are recursive. They take their own sweet time to converge. So, the rate of convergence is important. What is it? The number of iterations required for an algorithm in response to a stationary input to converge close enough to an optimal solution. Algorithm of high rate of convergence adapts rapidly to a stationary environment, and it is important for us to have a fast rate of convergence. The second point is misadjustment. What is that? It provides a quantitative measure of the amount by which the final value of the mean squared error averaged over an ensemble of adaptive filters deviates from the optimal mean square error. Computational complexity, important. Number of observations required to make one complete iteration of the algorithm. It will clearly be correlated to the energy your equalizer consumes. Numerical properties. Certain algorithms are prone to inaccuracies like round of noise and representation error in the computer and your fixed point operators. So, many times you do not have floating point operations possible in your digital signal processors or things like that, or round off errors or the finite length quantization, etc. So, those may lead to unstable algorithms and a slower rate of conversion. So, these are the 4 important aspects we must keep in mind while picking up a certain algorithm. Now, let us briefly talk about the important algorithms. The 3 most popular ones are the zero forcing algorithm, the least mean square algorithm or the LMS, and the recursive least square or RLS algorithm. Please note these are applicable both for the linear and the nonlinear equalizers. First, let us talk about the zero forcing algorithm. Here the equalizer coefficients Cn are selected so as to force the samples of the combined channel and the equalizer response to 0 at all but one of the NT-spaced sample points in a tapped delay line. What does it mean? It means it is trying to simulate the Nyquist condition, wherein other than its own sampling instance, for all other instances it is forcing the value of the symbols to be 0. So, here is the combined impulse response as expected for any adaptive equalizer. H channel f, H equalizer f is equal to 1. The disadvantage is as follows. Since the H channel is inverse of H equalizer, so the inverse filter may excessively amplify noise at frequencies where folded channel spectrum has high attenuation. So, the zero forcing algorithm is not used for wireless links except for static cases. It was originally invented for wireline applications, so it is normally not used. A more popular one is the least mean square algorithm, also called the LMS algorithm. The LMS algorithm is based on minimizing the mean squared error between the desired equalizer output and the actual equalizer output. So, it works purely on minimizing the MSE. The prediction error is given by Ek, given by dk minus dk hat, right, which can be expressed as xk minus yk transpose. These are the delayed, this is the vector transpose of the delayed inputs, and this is the weight vector wk. The mean squared error is nothing but expected value of Ek complex conjugate Ek. Now, we define for the first time a cost function j as a function of the weight n represents the mean square error. Then, in order to minimize the mean squared error, its derivative of j should be 0. So, del j omega n, this is Wn by delta Wn should be equal to 0, and you get this famous normal equation where you have to put R nn, the input covariance matrix, times the weight vector equal to the Pn. This is the correlation between the expected xk and the yk, the received vector. If this is set, the minimum mean squared error of the equalizer is given by the following equation. So, if you use LMS algorithm, this is what you expect to get in terms of the minimum mean squared error. So, to get an optimal tap gain vector W n hat, J opt is solved iteratively. That is where the recursive nature comes until it converges to a small value. This is what we are working with. Practically, MSE is minimized by stochastic gradient algorithm, also called the least mean square LMS algorithm. If n denotes the sequence of iteration, then LMS is computed iteratively by these following equations. Today these are fairly standard, and you can get your weight vector by following. Here n is the number of delay stages in an equalizer, and alpha here is the step size which controls the convergence rate and the stability. If you increase the alpha, the rate of convergence increases, but your stability, it will not finally settle down to the close to the optimal value. So, alpha is usually adaptive, it can be changed on the fly. Let us now come to the final RLS, or recursive least square algorithm. This is an adaptive signal processing technique for rapid convergence rate. LMS is usually known to be slow. RLS on the other side is a much faster technique. Here error is measured in terms of time averages of actual received signal rather than the statistical averages of RLS. Here the least square error based on time average is defined as follows. So, this is what we have to minimize. See, in LMS algorithm, if the eigenvalues of the input covariance matrix lambda vary too much, that is lambda max over lambda min is much greater than 1, it will take a long time to converge. So, we have to put that thing into effect, which is done by the RLS algorithm. The error is given by the following equation: xi minus delayed version vector and the weight vector, and the data input vector is defined as follows. To get the minimum least square error, the derivative of Jn is set to 0. And here in this slide, RLS minimization leads to the following weight equation. So, we are not going through the whole derivation. Again, you can consult Proecus Digital Communications to go through the derivations, but this is the final crux of the matter. This is the weight vector definition. Here Kn is given by this following equation, and RNN inverse can be expressed as follows. This is the input covariance matrix, and mu n, which is used here, can be found by this method. So, let us now summarize today's lecture. We started off with a brief survey of equalization techniques, then we moved on to linear equalizers. We then looked at nonlinear equalizer structures and talked about the decision feedback equalizer, the maximum likelihood symbol detection, and finally the maximum likelihood sequence estimation. We also looked at 3 important algorithms for adaptive equalization: the zero forcing algorithm, the least mean square algorithm, and the recursive least square algorithm. We will conclude our talk here.